Bismillahirrahmanirrahim. This is Janki Badar Sumra, Assistant Professor at Electrical Engineering Department, Sakraib University. Today, we will discuss on one of the technical paper titled Design and Control of Modular Multilevel Converter for Voltage Sag Mitigation. This paper is published in MDPI Energies, 24 February 2022. Voltage sag in a power system is an unavoidable power quality issue, and it is also an urgent concern for sensitive industrial users. So this is true that voltage sag is sometimes a very serious critical power quality issue that should be addressed. To ensure power quality demand and economical operation of the power system, voltage sag management has always drawn great attention from researchers around the world. The latest research that realizes the power quality conditioning has used dynamic voltage restorers, static VR compensators, adaptive fuzzy inference systems, and fuzzy logic controllers based on DVR to mitigate voltage sag. Now, these are some of the approaches to mitigate the problem of voltage sag, and they are discussed in detail in this paper. These devices, methods, and control strategies that have been recently used for voltage sag mitigation have some limitations, including high cost, increased complexity, and lower performance. So these are the drawback of these methods. This article proposes a novel, efficient, reliable, and cost-effective voltage sag mitigation based on a MMC that ensures effective power delivery at nominal power under transient voltage condition. All right. So basically, in this paper, MMC-based HVDC system is proposed that can mitigate the problem of a voltage sag. I mean, even if the voltage sag happens at the point of common coupling due to some fault on the grid side uh, converter, the fault may be uh, due to different reasons. It may be a symmetrical fault or asymmetrical fault. Voltage dip can come due to several reasons. So whatever the reason is of the voltage sag, but the proposed MMC based HVDC system shall be able to mitigate that issue of voltage sag, and during that voltage sag the energy missing will be supplied by energy stored in the capacitors. I mean, one of the inherent property of the MMC is that MMC can store energy in some module capacitors. So overall energy is stored in the MMC. So that energy will be utilized to compensate the missing energy due to the voltage dip, due to the voltage sag. All right. So even after the voltage sag, the power delivered to load will be constant and it will not be affected. So loads are not going to get any kind of disturbance. Loads are going to get the power they desire, the constant power that they desire, instead of this voltage sag. So this is the advantage of this MMC based HVDC system. The proposed method, the MMC compensates for the energy loss caused by voltage sag using its internal energy storage of the submodules and ensure reliable power delivery to the load distribution system. This is what I explained. That even during the voltage sag, inherent internal energy storage in the submodules capacitors will be utilized to compensate that missing energy of the voltage sag, and it will be ensured that reliable power delivery is it will be ensured that the power delivered is successful and reliable to the load. Furthermore, control strategies are developed for the MMC to control DC voltage, AC voltage, active power, circulating current. So these are circulating current is coming into the internal dynamics control, and these DC voltage, AC voltage, active power, these are the outer loop controls. So in this paper, outer loop controls and internal dynamics control like circulating current will be discussed in detail. Detailed system mathematical model of controllers are developed in the dual synchronous reference frame theory. We will discuss in detail in the paper about DSRF. Validation of results of back-to-back for dynamic load distribution system is analyzed, which proves the effectiveness of the proposed scheme for voltage sag mitigation. So results will prove that yes, the inherent energy storage of MMC is utilized and the load is given the constant power supply even after this voltage sag, and this voltage sag mitigation will be ensured. Okay, voltage. What is voltage sag? Basically, a decrease in RMS voltage from 10% to 90% of nominal value for the duration of 0.5 cycles to 1 minute. Now, basically, uh, it's a decrease in the RMS voltage from 10% to 90% of nominal value for the duration of 0.5 cycles to 1 minute. But different countries have uh, different standards for the voltage sag. So this table refers to those standards. Uh, there are different techniques. MMC-based HVDC system is one of the technique to mitigate the voltage sag. But apart from them, uh, we can also use dynamic voltage restore (DVR), as we see here. If there comes here the uh, voltage sag, if there comes a fault in AC grid, and due to this, if there comes a voltage sag over here, even then DVR will make sure that the load is continuously getting the constant power which is desired, and this missing energy will be will be supplied by this DVR. So some researchers are using SVC. The approach and method is different, but the concept is same. And some researchers are using unified power quality conditioner. Here is a comparison of these different methods. Now in this paper, MMC is utilized. Here I would quickly mention that MMC modular multi-level converter is considered to be the one of the robust power converter topology and is preferably used due to its silent features such as reduced total harmonic distortions, improved power quality, and there's no need of filter. It offers modularity, it offers scalability, and it offers fault right through capability. So due to these advantages, MMC is preferred converter topology. All right. MMC can be designed to operate continuously in alternating mode with satisfactory power quality. The voltage spike in upstream grid caused by asymmetrical fault can be successfully mitigated by using MMC to ensure satisfactory power delivery to the load distribution system. Using modern MMC technology, this paper presents a novel approach to efficiently mitigate voltage sustain in upstream AC systems. I would like to mention here that this paper is totally inspired from the CERN thesis work. So, if you are interested in this research area, I would recommend you to also study uh, a thesis which is on this topic, performed by a student who has worked in CERN for a year. In my next video, I will also discuss on the work of that student who has worked in the CERN organization for a year of 1 year in this field. All right. The following contributions are summarized in this paper. An analysis of an MMC component dimensioning and control system is provided, followed by consideration of whether an MMC can be specifically designed for dynamic load distribution, ensuring power quality. So MMC component dimensioning is performed. I mean, what should be the apparent power, what will be the how many submodules are needed, what should be the value of capacitor dimensioning, capacitor sizing, arm inductance, these things are performed. The article explores the feasibility and potential of MMC to mitigate voltage sag due to asymmetrical fault in upstream AC grid side and to deliver constant power to load distribution. In results, we will see that even after the AC grid side, there will be a voltage dip, but the load will be continuously getting constant power. So the third contribution is the paper examines the effect of voltage sag of magnitude of to minus 60% for 75 millisecond. So dip severity we can imagine from here, we can get from here that it's a minus 60% dip for 75 millisecond in upstream AC grid when using the internal energy storage of back-to-back modular multi-level converter. Okay. Uh, Now we will discuss MMC component design principles. It requires extensive planning to design MMC, including sizing and dimensioning of its components. The design procedure of MMC include determining the number of submodules per arm, DC link voltage, submodule switching devices as per industrial standards, and rating submodule capacitance, and arm inductance. So the formula for apparent power is under 3 into V line to line into IRMS. Here from we can calculate apparent power. DC link so this is a flow chart. After apparent power, uh, we can calculate mathematical equations for DC link voltage. We should know about the submodule capacitance. What should be the submodule capacitance? What should be the submodules per arm? What should be the value of arm inductance? Because if these values are not properly selected, the system will behave like the system will not give the desired results. The DC link voltage of modular multilevel converter determines the average voltage of some module capacitor. Okay, so average voltage of some module capacitor depends upon the DC link voltage. What is the current DC link voltage. The rating of semiconductor-based RGB technology limit the average voltage VSM of some module of the MMC. The DC link voltage of MMC can be determined by multiplying the average voltage of capacitor with total number of some modules per arm. All right. So, if suppose we are designing HVDC system, there should have HVDC DC link voltage of 640 kilovolt. So, in this case, if we add all these upper submodules capacitance values, so C sum capacitance sum value, uh, the voltages in the capacitance of the upper arm should be having the value closer to the 640, but there will be little bit ripple included in it. So DC link voltage of the MMC can be determined by multiplying the average voltage of capacitor with the total number of submodules per arm. So if you multiply the total number of submodules per arm, then multiplying the average voltage of capacitor, the DC link voltage MMC can, so you can measure the DC link by multiplying the average voltage of the capacitor with the total number of submodules per arm. Okay, taking into account standard current and voltage ratings of semiconductors, the submodule capacitor acts as an energy buffer, and its capacitance dimensioning is necessary for energy storage calculation. So this is true because in this case, this capacitor dimension plays a very important role because the missing energy due to that voltage sag will be provided by this energy stored in the capacitor. The capacitance of the capacitor of some module should be chosen with a low level of voltage ripples. Yes, we have to ensure that capacitor voltage ripple problem should be reduced. If capacitor voltage has a lot of ripple, then the issue is that the circulating current will also increase, and if it will be continuously capacitor voltage ripple will increase, or circulating current will increase, then overall it will result into instability of the system, and system will fail. So it is always desired to have reduced circulating current, and it is always desired to have reduced capacitor voltage. All right. Arm inductance of the MMC is required to limit the circulating current in the arms, short circuit current, and to isolate the lower and upper arms of the MMC. Yeah, this is very true. Basically, one of the reason arm inductance is used is to basically limit the circulating current. And other reason is if there happens a very critical fault, DC pole to pole short circuit issue. So due to this DC pole to pole short circuit issue, a very high DC current will rise up, and that short circuit DC current is limited by this arm inductor. So this is another reason we use arm inductor. Uh, but uh, but we cannot totally eliminate the circulating current depending on the on an arm inductor. We cannot totally rely on the arm inductor for eliminating the short circuit current, DC current due to DC pole to pole short circuit. But we have some other digital control schemes and other protection schemes used. But for some few, arm inductance will limit it up to certain time. According to the ideal relationship between AC and DC side of the MMC without taking account of internal losses, actually PDC is equal to PAC. So if we ignore the internal losses, so DC power should be equal to AC power. This is the expression for PDC, this is the expression for PAC. Here from we can write the expression for I phase. Here we can find out the value of VDC. So this is the DC link voltage of modular multi-level converter, which is a direct relation with the RMS value of AC grid. So if you have more DC link voltage, then if it is working as an inverter, more a line-to-line RMS voltage can be expected. And it has inverse proportion with the modulation index of the converter. That means that if due to some reason there comes a dip under voltage in the HVDC DC link voltage, this value gets to under voltage, this value is reduced due to some reason, then certainly the inverter has to operate in our modulation. So this is one of the issue. So we do not want this DC voltage to go for under voltage. If it goes for the under voltage, then inverter has to operate in our modulation, which is a problem. And if this DC voltage due to some reason, if it goes to our voltage and power imbalance happens and this rises up very high, then it can also trip all the MMC stations. It can trip the HVDC system, and this is also not recommended. So recommended approach is that whatever the desired DC link voltage is, we have to make sure the desired link voltage is strictly being followed and regulated. So this is the purpose. Okay. The submodule capacitance, the capacitor of the submodule is the main component of the converter which acts as energy buffer. Energy is stored in this capacitor. Sizing and dimension play a vital role while dimensioning the submodule of the capacitor. The capacitor of submodule is floating in nature, owing to its charging and discharging by converter arm current. This is true. Converter arm current flows through the capacitor and it charges up and discharges. And due to this charging and discharging, we get capacitor voltage ripple, and the arm current causes inevitable voltage ripples which have an inverse relationship with the capacitance of the capacitor of the submodule. Choosing a reasonable capacitance of a capacitor for submodule can reduce the magnitude of voltage ripple. Capacitor voltage ripple can also be controlled by eliminating the harmonics in circulating current. Yeah, basically the circulating current and capacitor voltage ripple problem has relationship. If what happens is that basically, let me discuss this point in a bit detail from one of my paper. All right. Actually, uh, during MMC operation, in MMC-based HVD system, the issues of circulating current and capacitor voltage ripple need to be closely examined. During MMC operation, the submodule capacitors will charge and discharge, which will cause capacitor voltage ripple issue, like we discussed now. This could result into energy difference between the upper and lower arm. It means that upper arm energy and lower arm energy will not be the exactly same in three-phase MMC. Now, due to this difference in energy, the potential difference, impedance voltage, and internal circuit between various phase legs arms are brought on by this energy difference. So this energy difference results into impedance voltage or potential difference and internal current. Now basically, uh, this internal current which flows due to difference in the due to energy difference in the upper arm and lower arm and overall difference between one leg to another leg. I mean, there are three legs in an MMC. Now, ideally, we want that the energy of these three legs should be very same. In other words, this potential difference among these three legs should be zero. But practically, uh, in spite of using voltage balancing algorithms to ensure that capacitors are equally charged and discharged, and the overall energy of the upper arm submodule and overall energy of the lower arm submodule of the capacitors are same, but even despite algorithms, practically 100% we do not get the ideal results. And due to this potential difference, now basically current flows. Let me show you in this figure 1. You see, basically this paper is in write-up process. Here you see, uh, now this is the upper submodule. This is upper arm. This is a lower arm. This is a lower arm. This is upper arm. This is lower arm. This is upper arm. This is lower arm. Total there are 6 arms. There are, and this is one leg, second leg, and third leg. Now, in spite of using capacitor voltage balancing algorithms, practically there is some difference in the upper arm capacitance energy and overall some of the lower arm capacitor energy. Due to this difference in energy, there becomes a potential difference, impedance voltage here. And this potential difference also exists between one leg to the other leg. So due to this potential difference, basically current flows. Wherever there the potential difference, current flows. And due to this potential difference, current flows from upper arm to lower arm and then from one leg to another leg. You can see these dotted rates showing the circulating currents. So these are the circulating currents. Now this circulating current which is flowing between the legs is basically AC component. And it was found out that if the grid is balanced, then this circulating current will be twice the fundamental frequency of the grid. I mean, if the fundamental frequency is 50 Hz, then the frequency of this circulating current was found to be 100 Hz. And due to this potential difference, it was found that this circulating current is a negative sequence component. So a lot of active research is going on to suggest different approaches to mitigate this circulating current, which AC component of circulating current. A lot of control schemes are being suggested for this purpose. Okay. So choosing a reasonable capacitance value is highly important. This is a mathematical expression to find out the capacitance value. And this is another way possible to find out the capacitance value. And determine some modules per arm is also important. As I already discussed that DC link voltage is equally distributed to n number of some modules per arm of an arm, the average voltage of VSM of a submodule is VDC by N. So average voltage of the VSM will be VDC divided by N with the total number of submodules. So if total number if DC link voltage is, let us say, 640, and total number of submodules are 40, so 640 will be divided by 40, so the average voltage of the capacitor VSM of a submodule capacitor will be that value. So if you have VDC and if you have average voltage VSM of a submodule capacitor, you can calculate number of submodules. So the biggest advantage of MMC is that it offers modularity. Modularity means that combining a smaller system to make a larger system. So I mean, in this case, MMC, hundreds of cells can be cascaded to achieve desired voltage and power ratings. So this n number of submodules can be hundreds in case of if you have a very high HVDC DC link voltage. So by combining a smaller voltage rating transistors, you can by adding them into cascaded, you can achieve a high DC link voltage requirements and power requirements using this modularity function of the MMC. So in market, different rating transistors are available. Like if you are interested to use 3.3 kilovolt, and say suppose you have DC link voltage of 100 kilovolt, so you will basically divide 100 kilovolt, and you have a transistor of 3.3 kilovolt, so you require in this case 30 number of submodule. Okay. Uh, it should also have redundancy and reliability. If any submodule due to any reason get faulty, another submodule should be inserted so that overall system should not be affected. So this is a redundancy, and MMC also offered this feature, arm inductance value. Arm is already discussed that arm inductor limits the circulating current, and it also limits the sudden rise of current due to DC pole to pole short circuit issue. So the proper selection of arm inductance is also very important. So these are the mathematical equations to calculate the value for arm inductor. Here it is also mentioned that arm current also limits fault current in case of DC link short circuit condition. We will discuss the remaining portion of the paper in our second part. Thank you.